Hello everybody! Today we're going to talk about why kinetic energy is 1/2 mass velocity squared. So when I was in high school, the textbook just gave this equation to me, but I thought, well, does it have to be 1/2 mv squared? Could we imagine a similar universe that's just like ours, except kinetic energy is like 1/3 mv squared? Could we imagine a world where it's 1/2 mv cubed? Do we only know this equation through pure experiment, or is there a way to theoretically calculate it? We can theoretically calculate it, and we are going to do that right now. The first assumption that we're going to make is that energy squared equals momentum squared speed of light squared plus mass squared speed of light raised to the fourth. We've mentioned this equation in another video, and it comes from Einstein's theory of relativity. The second assumption is that the speeds of our objects are going to be much, much smaller than the speed of light. In other words, we are in the classical limit. The third assumption is that momentum equals mass times velocity. As a reminder, this equation only works for a massive particle in a classical situation. And just to be clear, by classical, I mean that we're dealing with sizes, temperatures, and speeds that you typically encounter on a daily basis. So we're not dealing with atoms or galaxies, but rather normal things like basketballs, automobiles, other day-to-day objects like that. The fourth assumption comes from mathematics. It says that when you have parenthesis 1 plus x parenthesis raised to the power of a, that is approximately equal to 1 plus ax, but only if x is much, much smaller than 1. This is what's called the binomial approximation. This equation comes from pure mathematics, so we can apply it to whatever temperatures, sizes, and masses we want. So let's start with the proof. We start by taking our first assumption and factoring out m squared c to the fourth, so we get e squared equals m squared c to the fourth, parenthesis p squared c squared over m squared c to the fourth, plus 1 parenthesis. You might notice that c squared over c to the fourth is just 1 over c squared, so we can rewrite this as e squared equals m squared c to the fourth, parenthesis 1 plus p squared over m squared c squared. Next, we take the square root, so that's e equals mc squared, parenthesis 1 plus p squared over m squared c squared, raised to the power of 1/2. As a reminder, square rooting something is the same as raising it to the power of 1/2. Alright, now it's time to use the binomial approximation. So since our speed is much, much smaller than the speed of light, and momentum is mass times velocity, that means momentum over the speed of light is going to be very, very small, which means momentum squared over speed of light squared is going to be very, very small, which means p squared over m squared c squared is going to be tiny compared to 1. So p squared over m squared c squared is like our x in this situation, and to the power of 1/2 is like our a in this situation. So let's use the binomial approximation to rewrite the equation as follows. And just to be clear, we brought the exponent 1/2 down so that it's being multiplied by the p squared over m squared c squared. This is the binomial approximation, and this is a mathematically proven approximation. Next, let's distribute. So the first term is mc squared times 1, or just mc squared, and the second term is p squared over 2m squared c squared times mc squared. The second term can simplify a little bit. The c squared over c squared is just 1, and then m over m squared is just 1 over m. So the end result is that we have energy is approximately mc squared plus p squared over 2m. So at this point, let's pause and think about how energy can come in many different forms. So what if the momentum were equal to 0 and the object were at rest? So if p equals 0, well then the whole p squared over 2m term is just 0. So what we're left with is e equals approximately mc squared. So if you've ever wondered where e equals mc squared comes from, it's from this equation. So we'll call this the rest energy, because it's the energy that an object has even when it's at rest, since the momentum is 0. And so in the classical limit, we see that this equation gives us two different kinds of energy. Now there's mc squared, which is the rest energy, but then there's p squared over 2m, which is the energy from motion, the energy from momentum. So what should we call this energy from momentum? Well, let's call that kinetic energy, or K, which is p squared over 2m. So finally, let's substitute p, momentum, for mv, mass velocity. So k equals mv quantity squared over 2m. That's just mass squared velocity squared over 2m. And so the divide by 2 is the same as 1/2, and the m squared over m is m. So finally, we have k equals 1/2 mv squared, which is precisely what we claimed at the beginning of the video. So as you can see, based on our assumptions about Einstein's theory of relativity and our equation for momentum, we are guaranteed to get that kinetic energy is 1/2 mass velocity squared. It cannot be anything else. If you learned something new today, please leave a like so that I know to make more videos like these. I just want to say that I deeply appreciate the positive response you guys gave to the previous 2 videos. As a physics teacher, it really makes my day to know that even if we're in completely different parts of the world, I was able to help you learn something new today. My next video is going to have a pretty different style from the first 3, so if you're curious to know what that'll be like, click the subscribe button so that you don't miss it when it comes out. Have a great day, everyone.